Example 16.5. In this example, we're going to talk about a common experience to feel chilly in the winter and warm in the summer in our homes, even though the thermostat is always set at the same temperature. This is due to the so-called radiation effect, resulting from radiation heat exchange between our bodies and the surrounding surfaces of the walls and the ceilings. We're going to consider a person standing in a room which is maintained at 22 Celsius at all the times. The inner surface of the walls, the floors, and the ceilings of the house are observed to have an average temperature of 10 Celsius in the winter and 25 Celsius in the summer. We need to determine the rate of radiation heat transfer between this person and the surrounding surfaces if the exposed surface and the average outer temperatures of the person are equal to 1.4 meters squared and 30 Celsius respectively. For this case, we're going to assume steady state conditions. We're going to neglect the effect of convection. We're going to assume that all the surfaces are maintained at a uniform temperature. The person is also completely surrounded by the surfaces of the room, and we're going to take all the properties to be constant. The fact that the person is completely surrounded by the surfaces allows us to write the rate of heat transfer for radiation simply as the amount of emissivity multiplied by the Stefan-Boltzmann constant, the surface area, and the difference of the surface temperature to the fourth minus the surrounding temperature to the fourth. In order to find the value of the emissivity, we go to the tables in the book, and we find in table 16.6 we find that the emissivity for the skin is given to be 0.95. The value of the Stefan-Boltzmann constant, it is equal to 567 times 10 to the negative 8, and this is watts m squared Kelvin to the fourth. The value of the temperature of the surface, which in this case is the body temperature, notice that is given to be 30 Celsius. And that is exactly the same both for winter and summer. And the value that is going to change is the surrounding temperature or the wall's temperature, which is equal to 10 for the winter and 25 for the summer. Okay, so now we're going to calculate each one of the values of the heat transfer rate and we're going to start for winter. So we're going to calculate the Q for radiation for the winter. Okay, we're going to substitute the value. So we got 0.95. We got the value of the Stefan-Boltzmann constant, 1467 times 10 to the negative 8 watts m squared k to the fourth. We got the value of the surface area, which was given to be 1.4 meters squared. And I'm just going to multiply the temperatures over here at the bottom. Please remember that the temperatures must be always in Kelvin. So we have the first temperature, which is 30 Celsius, and we do 273 to the fourth minus T surrounding for the winter is equal to 10 Celsius plus 273. And this is to the fourth, and then the final unit of this is going to be k to the fourth. For each one of them, it's going to be k to the fourth. Once we substitute the values in the calculator, we find that the heat rate for the winter is equal to 152 watts. Okay, so now we do exactly the same process. The only difference is that we are going to change the values of the temperatures. So now we calculate the rate of heat exchange for the summer. So we substitute the same quantities. 95 for the emissivity, 567, negative 8 watt m squared k. The surface is exactly the same, it's the same person, the same area. The body temperature is exactly the same, so it's 30. This is to the fourth. Now the only change that we have now, it is going to be the surrounding temperature, which in this case for the summer is equal to 25 Celsius. And once again, we make it into Kelvin, and this is to the fourth, and the final unit is going to be Kelvin to the fourth. We calculate the values, and we find that the value of the heat rate for radiation for the summer is equal to 40.9 watts. Note that the value of the heat transfer rate for radiation in the winter is about 4 times higher than the one that you will have in the summer, even though the body is maintained at the same temperature. That means that you're losing 4 times more heat, and that's why you will feel chilly in the winter, even though technically you are at the same temperature in the winter and in the summer. And that's what is known as the radiation effect.